So this chapter 6, we're looking at scatterplots and what scatterplots do. Um, we're going to be looking at relationships between two quantitative variables. So we're still on the quantitative variable kick here, and we're going to be looking at relationships between two of these quantitative variables. So we have a scatterplot here. And so you can see the X variable is the year, the Y variable is the prediction error, however that is measured. And so if you plot this over the years from 1970 to 2010, for example, we can see if there's any pattern. And as you can see, this pattern is kind of going down as the time goes up. And so we call that like a negative pattern. We can also look at how strong the relationship is or how weak it is, and that kind of thing. We can see if they're outliers, and so we'll see how to do all that as we go along. So a scatter plot is just something that exhibits the relationship between two quantitative variables. And it is used for detecting trends and patterns. So as you can see here, we can kind of notice a pattern. It seems to be going down over time. So that's one of the things that we'll kind of be looking for as we talk about these. So we can talk about the direction of a scatter plot. So a negative direction, we just kind of have a picture here of what that looks like. And of course, this one also kind of follows that pattern. So negative direction means as one variable goes up, the other, let's try that again, the other tends to go down. Or we could say we have a positive direction, that'd be the other way. And then as one variable goes up, the other one tends to go up. All right, and then no direction. I don't know if we need to write anything, but knowing if one goes up, the other one could go up or down. And so that doesn't really tell us anything. We can see no direction. There's just kind of chaos on the scatter plot and can't really learn anything other than there's probably no relationship there. Then we can talk about the form. And I won't really say too much about this, but we'll just kind of label these. So we have linear form, and of course, linear just means it's in a straight line. It's pretty much a straight pattern. Here we have a curved relationship, and this would kind of look like an exponential function if we were in algebra. So it curves, and it either curves up, or we could have one that curves down like that. And then we have curves up and down. And so this one would look more like a parabola. So it goes up for a while and then comes down, or vice versa. We could go down for a while and then come back up. So either way. Then we have the strength. So the strength is talking about how close are these points together and how strong is the pattern, how easy is it to predict what will happen in the future. So here we have a strong pattern. We could have very strong if they're almost in a perfect line. Then we have moderately strong or moderate, and then we have weak. And so the weak is just there's no direction, there's no form here, no strength. Moderate, we can definitely see a pattern, but it's not very strong. They're not close around a line that might go through them. Whereas these, if we drew a line through these, they're all pretty close to that line. These, if we draw a line through those, we have a few that are out here that are not so close. They don't really, not bad points, I wouldn't say, but not super close either. Then we have outliers. Outliers, these are basically the same thing as what we saw in chapter 2. But now we're kind of in a two-dimensional world. So we're going to say this a little bit differently than what we said before. So in chapter 2, we defined outliers as points that are far from the rest of the data. In this chapter, outliers are points that don't fit the pattern. Points that do not fit the overall pattern. So they could kind of be far from the data, but they still fit the pattern, in which case they wouldn't really be considered an outlier. So let's look at a few examples and we'll see what we can tell from these. So we have cost of women's clothes versus food cost. So as you can see, positive association. So if we were to draw a line to this, it'd have a positive slope. The association is pretty straight. We're not curving in any direction. Possibly a few high outliers. Now, what we're talking about here, probably these might be considered outliers. Maybe this one. But if we draw a line through it, it probably would look something like that. So this one, even though it's kind of far from the others, it still follows that pattern. And so I don't think we'd consider that an outlier. Maybe that one is getting a little bit out there, but that's not, I don't think that one's too bad. So probably these three, maybe that one, and maybe this one might be okay, but you get the idea. So we're kind of looking away from the line in either direction, but not one that would be on the line if the line went far enough. Moderately strong correlation, so we can definitely see the pattern, but they're not really tight around the line. And then the positive association just means higher clothes costs correspond to higher food costs. So as one price goes up, the other tends to go up as well. All right, looking at the next one, comparing prices worldwide, average hourly wage versus hours to earn an iPhone. So how many hours you have to work in order to purchase an iPhone. And this one, so negatively associated. So as the hours that you work go up, or as your wage goes up, the hours you need to work to buy something goes down, which of course makes sense. The more you work, or the more you make, the less you have to work to get an amount of money. So there's a negative association. This is a very strong correlation. If you draw a line through this, all of these points are pretty close to that line. And even this one that is kind of the farthest one away, that's still really close. So then association is not straight, it's definitely curved. Higher hourly wage corresponds to fewer hours to earn an iPod. All right, let's look at number 3. So here we have a little bit less going on as far as a pattern goes. Clothes index and working hours index is very weak, I would say. Although you can tell that it's kind of going down, but if we draw a line through that, we have a lot that are far from this, and maybe even I might draw it down here, but still generally going down. Generally straight, definitely negative. And knowing the working hours per year does not tell us, I mean, I guess it tells us something. Working hours, if the working hours are high, the clothes index tends to be low, but I don't know how good of a prediction we can make, especially with these up here. I mean, the working hours is going up, but these are also still up. So, and then we have some down here where the working hours is down and the clothes index is down. So not everything typically follows the pattern. And so that just indicates there's a weak association. All right, so if we move along, let's talk about the roles of variables. So we have 2 different variables here. And so we have an X variable and a Y variable. The Y variable is the one that we are always going to predict. So you use the information from the X variable to predict the Y variable. And either you might be able to switch them and make a prediction based on the other variable, but whatever variable you name as X is the one that you're using to predict Y. It's always the way it's going to be. So let's look at these examples here and decide which variable would be the response, which is the Y. So response is the Y, explanatory is the X. And I always, when I do this in class, what are the two variables? First of all, that's probably what we need to pick out. So do baseball teams that score more runs also sell more tickets? So runs would be one variable, tickets would be the other variable. And which would you use to predict the other? So I would say, and you can kind of look at this, sometimes the way you decide is which would come first. And the way the question is worded can usually indicate which they're considering to be first and which chronologically which comes second. So in this case, more runs seems like it comes first, more tickets seems like it comes second. And the reason I say that is because you don't want to, we're going to talk about causation in a minute, and you don't really want to assume that X is causing Y to go up or down. But you can use which one comes first and make a prediction on the one that comes second. And so that's kind of what we're doing here. But we're not assuming that scoring more runs causes more tickets to be sold, although that could be the case. But that's not what we're saying here, and that's not what we're looking at. All right, number 5 says, do students with higher SAT scores get better grades? So we have SAT scores and we have grades. And so we're kind of, the way the question is phrased, SAT scores seem to be coming first. And so we're going to call that one X and call this one Y. Number 6, can we estimate a person's BMI by measuring the wrist size? So we have BMI and we have wrist size. And in this case, we're going to estimate the BMI. So that one has to be the Y. We're estimating something, it has to be the Y. That's always what we're estimating. That's always what we're predicting. Okay. All right. So correlation coefficient. Oops. Let's go back. Correlation coefficient. So this is a numerical measure. It's a way to exactly measure the relationship between two variables. So before we've kind of said this looks strong, this looks kind of moderately strong, this looks a little bit weaker. With a correlation coefficient, you can quantify that measurement of the relationship. So to use R, there must be a true underlying linear relationship. So this only works with linear relationships. It doesn't work if it's curved, it doesn't work if it's a kind of parabola type relationship. Variables must be quantitative, so we cannot do this with categorical variables. Pattern for the scatter plot must be reasonably straight, and then outliers can strongly affect the correlation. So even if you have one outlier, depending on how far out it is, but if you have an obvious outlier, that's going to drastically affect the correlation. And so, like we talked about in chapter 4, look at the outlier, see why it is an outlier, if it's an error, that kind of thing. So those are highly effective on the correlation. All right, so number 7. So this is the same scatter plot we saw earlier, and let's talk about this with correlation. So the scatter plot indicates a straight line pattern. Variables with quantitative, no strong outliers. We did say maybe these, maybe that one, they might be considered outliers, but they're not strong outliers. They don't just completely stand out. As if you had one up here, that would be a very strong outlier. So no strong outliers. Correlation of R equals 0.614 is moderately strong. So we'll talk about the values of R in a minute and how what's a good value, what indicates a weak value, that kind of thing. So we'll do that in a minute. Number 8, wage in iPhone. So this scatter plot is not straight, so we cannot even do a correlation coefficient there. So the correlation coefficient would indicate it's a very weak association if you try to do it with one that's not linear. So not wise to do it in that case. And then the next one that indicates a weak negative association, you can still, so if it's a weak association, you can still do a correlation coefficient because it's not, I mean, I guess it kind of is linear, but even if it's not, I mean, it has to be pretty strongly not linear to do it when there's a weak association. So usually if there's a weak association, you can still find a correlation coefficient just to kind of prove what you can see from the scatter plot. And in this case, negative 0.388 represents moderately negative or moderately weak negative association. All right, so looking ahead, properties of correlation. So R, let me probably figure this out anyway. R being positive indicates a positive association. So if R is positive, there's going to be a positive direction in the scatter plot. If R is negative, there's going to be a negative direction in the scatter plot. And R is always between -1 and 1. If R is -1, or if R is +1, you would have, so let's say the R is +1, you would have a scatter plot that is exactly in a straight line, just like that. So that, well, if that was in a straight line, so you know what I mean. R equals 1, it'd be perfectly on a straight line. Now, that's not saying anything about the slope. So you could have a slope like that. You could have a slope like that. That would still be R equals 1. So the slope is not what we're talking about. We're just talking about the strength, and it is a positive slope. But the slope could be 10. It could be 0.5. All we know is that it's positive, and if R is 1, we know that they lie on the line. And so the closer it is to 1, or the closer it is to -1, the more tightly they will be, the stronger that relationship will be. And then the closer they get to 0, the less correlation there is. So R equals 0.1, -0.1, something like that, where we're getting close to 0. That means you'll just have no pattern at all. Or, I mean, I guess it is possible if you had the curved scatter plot where it's coming down like that, and very strong association, but you cannot do the correlation. If you try to do the correlation with that, it probably would be close to 0 because it's only measuring linear. So that's kind of how you interpret the R and how you decide. And there's no real boundary. Like if it's above 0.7, we consider that strong. If it's below, between 0.4 and 0.7 or whatever, we consider it moderate. There's no agreed upon boundary for that. So it's kind of up to interpretation. But generally speaking, the closer you are to 1, the stronger it is. The closer you are to -1, the stronger it is. The closer you are to 0, the weaker it is. All right, so then interchanging X and Y does not change correlation. And that's because we're talking about a relationship between two variables. So if I'm standing 10 feet away from you, that's our physical relationship. We're 10 feet apart, and then we switch places, we're still 10 feet apart. So the physical relationship did not change. That's the idea there. R has no units. And since R has no units, changing the units of X or Y does not affect R. There's really no way to affect R other than adding more data. If you add more data, then R would be affected a little bit or a lot, depending on the data. But if all you're doing is kind of shifting the data, scaling the data, like we talked about in the last chapter, that's not going to change R. Correlation is sensitive to outliers, and then correlation measures the strength of the linear association. All right, and then last little topic, correlation does not equal causation. And so that's a very easy thing. Like we've all probably heard that phrase. And it's a very easy thing to kind of forget, and you start seeing these correlations and you think that one is causing the other. So just as an example, storks and babies, we have a scatter plot here. There's a clear positive association. R is 0.97, so that's very close to 1. So that's going to be very strong positive correlation. But does not prove that an increase in storks causes an increase in babies. So that's just one example. So what's the reason for the correlation? It could be that Y is causing X. Maybe if you switch them, you could say that one is causing the new X is causing the new Y. Or there could be a lurking variable that is causing both. So there could be a third variable that we're not considering that's causing X and Y to move together. So for example, the number of gray hairs and the number of wrinkles are strongly correlated. But if you dye your hair black, it does not get rid of your wrinkles. And the lurking variable, of course, is age. So the older you get, the more gray hair and wrinkles that you get. So all right, so the one thing I don't have on the notes, we need to do an example for creating a scatter plot on the calculator. I'm going to attach a YouTube video, and that will show you how to do that. So make sure you can create a scatter plot on the calculator. That's probably one of the most difficult things. I mean, it's one of those things that it's easy to get an error doing it. It's not super hard. If you know what you're doing, you can do it. But it's very easy in the beginning to get an error trying to make a scatter plot. And so I'm going to post a video. If you have questions, I can try to walk you through that as well. So I will see you on the next video. Email me if you have any questions at all.